Let's start with that process again. F prime leads to critical points, which we put on a number line, which tells us increasing and decreasing, which tells us relative max and min. I know what we'll do. At the end of the lesson, we'll come back and we'll put the parallel thing for the second derivative. Because there's going to be a nearly identical path. There's some different words because they mean different things if we're talking about the second derivative, but it's going to be the same process. So today is easy in terms of process because it's the same process. It's maybe trickier for concept because it's all these different words that tell us different things. Okay, that's the lead in. Function analysis, concavity, and points of inflection. Consider the graph shown below. It's the same graph we've been working with this entire unit. Concavity, you're familiar with concave, convex, like from physics, concave lenses, concave mirrors, convex. We don't do any of that. If I do, I die, and hi-ho equals negative dido. Does that sound familiar? Some of you know. If you had physics, it ought to sound familiar. Concave, convex. You've at least got that much. We don't worry about convex. We'll only talk about concave down versus concave up. And I think it makes sense. Concave down is like a frown. So it rhymes. Down like a frown. Concave up like a cup. Concave up could hold water. Concave down, you'd be dumping out the water. It's another way to think of it. And so again, visually, it's pretty easy to see. Why don't we do the thing we did earlier where we highlight some things? Let's concave down. Let's highlight all of those things with one color. So pick your color. Anybody like me to throw a highlighter at them? Like gently at them? Like going deep here. Yes. And I'm out, so you're on your own now. Oh, I got one more. Anybody else? Sidearm delivery there. Okay, so I said concave down was yellow. It doesn't matter your color. So down like a frown. So that would be concave down. This would be concave down. There's a sharp point there, but that's still down like a frown right here. So there's my concave down spots. And pick a different color. Threw out all my good colors. For concave up. Up like a cup, could hold water. So all the other spots would be concave up. So, like increasing and decreasing, max and min, like if you have the picture, it's pretty easy to just look at the picture and see, oh, there's a max, there's a min, there's concave down, there's concave up. A point of inflection is a point on the function where the concavity changes. So, point of inflection is where concavity changes. From upward to downward or downward to upward. So all of those dots on there are points of inflection, which we frequently abbreviate POI. Point of inflection, point of inflection. All those places where it changes from being down to up are points of inflection. All right, draw some tangent lines to the graph on a section of the graph that is concave down. Okay, so for us, or for me, concave down was the yellow section. So some tangent lines on the concave down section, or there's a little picture here, it's maybe hard to see. And then just kind of hold that thought, although now I'd ask you the question, what do you notice about every tangent line on the concave down sections? Where are they located relative to the curve? They're above above the curve. The tangent lines are above the curve, lie above the curve. And then on a concave down section, all the tangent lines, on a concave up section, all the tangent lines lie below the curve. That's not something you memorize. If we ask that, that's something you sketch out and you draw, and you're like, oh yeah, they're all below, or they're all above. So that's not one that you memorize. Definition of concavity. Let f be a differentiable function on an open interval I. The graph of f is concave up on I when f prime is increasing. Okay, f prime increasing means concave up. Slope is increasing. Think about what that means. So maybe if it starts at 0, but then it increases a little bit, and increases a little bit more, and increases a little bit more, if the slope is increasing, f prime is slope, then you're concave up. Concave down when f prime is decreasing. Again, if you started at 0, but then you go a little bit negative, and more negative, and more negative, that would be concave down. So now we have to be careful, because if f prime is positive, that means the function is increasing. If f prime is increasing, that means the function is concave up. So we have to be super careful about f prime being positive versus negative, or increasing versus decreasing. If f prime is increasing, what can we say about f double prime? We would say f double prime, let's see, if f prime is increasing, f double prime is, you could say that is the slope of f prime, if you think of it this way. And if f prime is increasing, then the slope of f prime is positive. So f double prime is positive. If f prime is decreasing, that means the slope of f prime is negative, then f double prime is negative. I'm going to try to put all this together later. Test for concavity. If f double prime is positive, then we're concave up. F double prime is negative, then we're concave down. Point of inflection is where the second derivative changes signs. Not enough that it's 0 or undefined, it's got to change signs. Let's go back up to the top. So when we take a second derivative, we'll set it equal to 0. Here's sort of the breakdown in our... there's not a name for critical points of the second derivative. The best we could say is they are potential points of inflection. Just like critical points are potential maxes and mins, but they have a special name. Potential points of inflection don't get a special name. But it's the same process. Once you set them equal to 0, you'll put them on a number line. That won't tell you increasing and decreasing. It'll tell you concave up and concave down. And where those changes happen are points of inflection. So it's a weird day that the process is nearly identical to what we did yesterday, but the conclusions are different. Instead of making conclusions about maxes and mins, we'll be making conclusions about concavity and points of inflection. First derivative tells us maxes and mins. Second derivative tells us concavity and inflection. Okay, some examples. Consider that function. Discuss the concavity of H. Concavity of H means I need H double prime, because that's what tells me about concavity. So I need to take a second derivative, and then we'll worry about all of those steps. So first derivative, let's see here. I have 4 pieces, so we'll pick on 4 people. McKenna, start us off. The derivative of negative x cubed. Negative 3x squared. Aslan, the derivative of 6x squared. Plus 12x. Seth, the derivative of negative 9x. Negative 9. And Johnny, the derivative of negative 1. 0. Okay. Yesterday we would pause here, set that equal to 0, put it on the number line, increasing, decreasing, maxes and mins. Today we're going to do a second derivative, which is nice for a polynomial because things get easier as we go here. So we've got 3 terms there. Caden, how about the derivative of negative 3x squared?
Negative 6x.
Negative 6x. Ava, the derivative of 12x plus 12. And Abby, the derivative of negative 9, 0. Okay, so there's our second derivative. Let's set that equal to 0. So subtract the 12, divide by negative 6. X equals 2. Again, that doesn't have a name. It's sort of the equivalent of critical points, but it's not a name. It's the potential point of inflection. Let's put that on our number line. Let's pick something less than 2 and greater than 2. And now I have 3 options to plug that in. I could plug that into H, or to H prime, or to H double prime. Which do you think we would like to plug that into? H double prime, because that will tell us about concavity. This is a second derivative thing. So let's find the second derivative at 0 and the second derivative at 3. So I'll plug in 0, I get 12. So that's positive. What does that tell me about H? If the second derivative is positive, be careful, it means H prime is increasing, which means H is concave up. Second derivative at 3, that would be negative 18 plus 12 would be negative. If the second derivative is negative, that means the original function is concave down. And by the way, the alternating thing still holds true, so you can usually just shortcut and alternate. Okay, what did it ask me to do here? Discuss the concavity. I don't think it wants like an essay. I think it just wants me to say H is concave up from negative infinity to 2, and H is concave down from 2 to infinity. Which means there's a point of inflection. It didn't ask for this, but there's a point of inflection at x equals 2. Is that what it's about to ask? Yeah. State the points of inflection. POI at x equals 2. Justify your answer. How did I know there was a point of inflection at x equals 2? Say it. The concave switch, yes. The point of concavity at x equals 2 because concavity switched. That's a good way to say it. At x equals 2. Hoping we get to a question like number 2 because it's always on the test and it always jacks people up. How many points of inflection does f have if f double prime equals x minus 2 squared, x minus 5? So what's different about this than what is normal? Okay, there's a double root. That's a good catch. What did they give us? They gave us the second derivative. It's like this is supposed to be an easier problem. We didn't have to take a derivative or a second derivative. Like they just told us, here's your second derivative. So if we set it equal to 0, we get 3 possible points of inflection. Now Bailey's going to let us shortcut this whole thing here. So how many of those are points of inflection and why? If you want to do the shortcut method here. Why are you telling me 2, Caden? You're right.
Because of the double root.
This one is not going to be a point of inflection because of the double root. So it's going to be 2. Now the longer way would be put those on there and test the intervals. Let's see, if I test something really big, that's easy to test. If I test 6, then everything's positive. If I test 4, then that one's negative. If I test 1, then that one is still negative. And this one is positive over here. That double root's not a POI. It didn't change signs because it's a double root. So there's only 2 points of inflection. So it's kind of an easy problem if you're paying attention and you realize, oh, they gave me the second derivative, so I don't need to do any derivatives. And there's a double root going on, so there's not, that would not result in a point of inflection. So that's an easy question, but like an easy, tricky question. Number 3, f of x equals 1/6 x cubed minus kx squared plus 1, k is a constant. If f has a point of inflection when x equals 8, point of inflection means f double prime changes signs. So that's what I'll be looking for. And k equals. So I need a first and second derivative here. Means I get to call on more people. Looks like there's 3 terms to deal with there. Work today. All right, Autumn, start us off. What's the derivative of 1/6 x cubed? 1/2 x squared. And this is another one where it's like, oh man, they gave me some fractions. And then you start peeking ahead and you're like, oh, they gave me some nice fractions. They're going to work out well for us. Ashlyn, how about the derivative of negative kx squared? Very nice. And then Dylan, from one extreme to the other, in terms of difficulty, the derivative of 1 is 0. All right, that's the first derivative, but we want a second derivative. Second derivative. Jameson, how about the derivative of 1/2 x squared? X. Austin, how about the derivative of minus 2kx?
Minus 2k.
Good, minus 2k. And we want that to change signs when x is 8. So basically we want it to equal 0 when x is 8. Looks like k would need to be 4. Yep, we need to do this page. We got time. This page, and then this will be it. Function analysis, second derivative test. You know what? Let's hold on a second. Try to summarize here. If f is concave up, then that means that f prime is increasing and f double prime is positive. Just putting this at the bottom of that last problem we did. If f is concave up, that means f prime is increasing. I have to think about this. Slope is increasing. F double prime is positive. That's concave up. So yeah, all of those mean the same thing. And then if f is concave down, it's like all the opposite things. F prime is decreasing, which means f double prime is negative. Again, you have to be super careful about f prime because we use increasing and decreasing on f prime, but we also use f prime as positive and negative. In fact, let's just put that on here. If f prime is negative, what does that mean? If f prime is negative, what does that mean? This is like separate. This doesn't mean anything about concavity. F prime is negative. So if the slope is negative, what is the function doing? Decreasing. And if f is increasing, phrase it the other way, what does that mean about f prime? If f is increasing, what's f prime? Positive. So we have to be careful about when we say increasing, decreasing, that's different than positive and negative, and we got to be careful if we're talking about f prime, and f double prime. So we got three different things: function, derivative, second derivative, increasing, decreasing, and there's all different stuff going on here. Okay, second derivative test. The first derivative test is what we did yesterday. F has a relative maximum where f prime changes, a relative minimum where f prime changes negative to positive, and a relative max when we change positive to negative. That makes sense. That's the number line. If we go from increasing to decreasing, we have a max. Okay, well, let's look at the graph of a relative maximum. So there's our max. We know that the slope of the tangent line changes from positive to negative. So like the slope of the tangent line changes from positive to negative. But what else is going on? Like specifically the concavity, especially when you compare the concavity of a max to the concavity of a min. What's the concavity at a relative max? Concave down. And the concavity of a relative min, this might seem backwards, but at the bottom of the cup, you're concave up. See, if a curve is concave down, must the curve have a relative maximum? This is a tricky question. If it's concave down, does it have to have a relative maximum? Well, this is a misleading graph. I could draw a concave down graph that just looks like this. So that answer is no. So we have to be careful. Same thing, if a curve is concave up, must the curve have a relative minimum? Well, if you think about the graph of e to the x, it's concave up, but there is no relative minimum. Okay, here's the second derivative test. If, I wish these were in a different order. I wish I could change that. I like these in a different order. If the first derivative is 0, that means if the first derivative is 0, that's a critical point, you've got a potential, that's a potential max or min. And then usually we put those on a number line and check for increasing, decreasing. But another way to do that is to check the concavity at those points. And so if we're concave down, again, I don't memorize these, I just have to think about them every time. Concave down looks like this. Slope of 0 looks like that. That results in a relative maximum. Concave down and the slope of 0, relative max. Concave up and the slope of 0, that would be a relative min. This is another box where I don't think you memorize that. When that stuff shows up, you start drawing little pictures and thinking about what it means to be concave down, what it means to have a slope of 0, and then you can figure out if you're at a max or a min. Some side notes. You have to meet both criteria for this to be true, right? It's not enough for there just to be concave down, and it's not enough for it to just have a slope of 0. It has to be both things. That's what all of that says. All right, 2 more example problems. Given g of x is twice differentiable, just means it has 2 derivatives. Oh, this is a lot of information. G of 4 equals negative 3. I'm going to try to draw this. G of 4 is negative 3. G of 4 is negative 3. G prime at 4 is 0. What does that mean? What's that telling me? G prime at 4. Potential max or min. The slope is 0. So I don't know what the graph is doing, but I know there's a horizontal tangent line there. Potential max or min. G double prime at 4 is 2. The 2 doesn't really do much for me, but the fact that it's positive, the fact that the second derivative is positive, what does that tell me about G? The second derivative is positive. It's concave up. So I don't know what this looks like, but it's concave up and it's a flat spot. Oh, well, I think I just answered the question here. That means there's a minimum there, a local minimum. So this type of question is like almost zero computation. It's just understanding, all conceptual, understanding what they give you. Same thing with number 2. Let f be a twice differentiable function. Selected values of the first derivative and the second derivative. Selected values of the slope and concavity. That's another way to phrase that. Right? Understanding what those derivatives tell you. Which of the following must be true? And all the questions are about maximums and minimums. Okay, well, the potential maxes and mins are where the slope is 0. And then if we are concave positive, there's a max there. This one's concave, whoops, I do that wrong. Concave up is a minimum. Concave up is a minimum. So there's a minimum at negative 3 and at 6. And I don't think I can make any other conclusions. I have to have a slope of 0 and a concavity, and then I can make some conclusions. Relative max? No, I've got relative mins. Relative min at 2, that's not true. Relative min at 6, that one's true. Okay, today's assignment is worksheet number 3, 1 through 13. You don't have worksheet number 3 yet, but I have it copied for you.